be a little bit more specific. You're trying to address a topic that's way too broad. But generally, it's good. So, I'm good. Some of it I've noticed also the style of referencing leaves something to be desired. So if I made a comment on referencing, anything like that, please go to the library, take a workshop, something like that. It's on you to know how to reference. This course is not about referencing. Okay? Are there any questions related to the proposal, topic, anything like that? I've seen a couple of places that the topic itself was ambiguous, like it says retaining walls. That's not good enough. It could be a stable, mechanically stabilized earth retaining wall, which I'm good with. It could be a reinforced concrete retaining wall, which I'm not good with. That's a different course. So, heed my comments that I left there. So next week, I believe we have the midterm, is it right? Okay, so we have a midterm. It covers, what it covers, like halfway through last week's lecture. The format is going to be very similar to the quiz. I'll ask a question, you answer it. And please answer the question. Not everything you know about everything, because, there's not a page for that. So be, just like I write here, be specific. I ask something specific, you answer something specific. That's all. We'll do probably an hour and a half. Okay? We'll do an hour and a half. And after that, probably both you and myself are tired of it, so we're not going to continue with the lecture. What I say is that in the break. What I'm saying is that there are two midterms in a course, so the two put together equivalent to a final. Hour and a half, 2 times, more than enough for me to see what you know. Okay? How to study? Anybody? Any guess how to study?
Read the PowerPoints.
Yeah, appreciated that a lot of things on the slides, there's some repetition, right? There's a good reason for that. Same, say, filters for dams. They fit into various categories, and there's a reason why they fit into various categories, because different aspects of it are important for different things. But the way to study would be just like he says, look at each slide, try to understand what I'm trying to tell you. Even though I gave you a recommended book or books, anybody bought it? Anybody has a copy? Good. The reason for that book is that if you feel that what I'm presenting here is not in-depth enough, like background and all that, that's what the book is for. Can you be A-okay without having the book? I believe I mentioned it at the beginning. Yeah, you can. But it's sort of like an insurance, because I'm not sure about other graduate courses, but most of them do not have a book. Some do, it depends. So, if you feel that, and this is particularly important for the second part of the course, for the derivation of the slope stability methods and so forth, the recommended book is a fairly good source. We'll see. I'll start probably the math today and putting the equations together, so if you're kind of rolling your eyes a little bit, then maybe finding a copy of that book or a similar book. I'm sure library has many copies of similar books. Find one, follow along what they say. So short, question answers. There's not really a calculation or anything, but as a good engineer, you always have your calculator with you. But, so pen, pencil, eraser, your head, that should be sufficient. Okay. So any thoughts, any questions about the midterm? We start at, 2:45, 2:50, if you arrive, and then go from there. Good. Any questions about the material itself that I covered last week? No, no questions. You guys are very shy. I guess after the first midterm, we're going to be much closer to each other, so the shyness will go away. I'm sure about it. So what you see, I started last week and now continuing, I'm kind of building up to this factor of safety, which is really the measure of a slope's stability. So prior to actually looking at the slope stability methods, you really have to have a good understanding of under what conditions we have to investigate this factor of safety. Because, you know, for even for a slope, and we'll see it in a moment, it makes a huge difference how we arrive at something that we call a slope. I can have a slope by having the level ground and building up earth and ending up with a slope, or I can have a slope by having the level ground and excavating down and building up, if you will, a slope. You end up with a slope both ways. Their behavior is completely different. You have a question? So, depending on how you're forming the slope, its behavior and definitely its stability can be different. It varies. Okay? So, factor of safety, just to recap for the nth time, variation of loads, shear strength with time. So some of them are indeed time dependent. So we have the capacity that may or may not change, and we have the load that may or may not change during the life of that slope. So just a simple example that if I have a saturated clay, everybody knows that what's carrying the load at the application of the load, like when you apply times zero. It is the pore water pressure, which time goes on dissipates, and more the soil skeleton, the soil particles are carrying the load, and eventually pore water pressure dissipates completely to the level that was prior to the application of the load, and we have our load carrying capacity. So, if we now look at the two examples, we have an embankment raised on a foundation soil that's a clay material. So let's just look at the statements first and then we investigate the figure. For embanking, building something up, the most critical time is at the end of construction. Okay, so that's statement number one. So we have to use the drained shear strength for sand, and we have to use the undrained shear strength for clay, depending on the soil. So let's look at this second one. Why do I have to use the drained for sand or undrained for clay at the end of construction? This is sort of the soil mechanics.
Because the pore water pressure doesn't affect the bearing capacity of the sand, and the clay is expected to be undrained all the time.
Okay, so what he's saying is that sands drain pretty fast because of their high permeability. So if I apply a load to sand, its undrained state is, a matter of seconds, right? It dissipates pore water pressure fast. So for sand, it would be a drained condition, essentially. The undrained state is really, really short. Whereas for clay, it can take years for it to drain. So end of construction, when I build the embankment, sands would be in the drain conditions because they drain fast, and clay at the end of construction would be well in the undrained regime. Okay? So going back to the first point, why is the most critical time at the end of construction? And to understand it, we look at the figure. So let's look at the first one. Horizontal axis for all, I guess 4 of them is time. The vertical axis is the load or pore water pressure or whatever. So let's look at the first one. As time goes on, I'm starting to build the material, so the height of the fill is going up, 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 up. and the vertical line here connecting all of them is the end of construction. I stopped building, I stopped embanking, and now the load stays constant. Is everybody okay with this? And the same, the average shear stress at point P or any other point is building up, up, up because the load is increasing, and then it stays constant. Right? Okay. So we can see that the actual load is going to be maximum or constant at the end of construction, and the load doesn't really change. So now let's look at the pore water pressure. Pore water pressure, it is what it is at that level below the groundwater table at point P. I'm increasing the pore water pressure because I'm increasing the load, right? It's undrained. It reaches its maximum at the end of construction, and since I'm not adding more load, it takes its time to go back to whatever it was prior to construction. So everybody okay with this? Figure number 3, we are not concerned at the moment. Let's look at the last one. So the last one would be the inclusion of the actual load and a pore water pressure, whatever the factor of safety equation is. Right now, it doesn't really matter. It is the capacity divided by demand. Okay, so the demand as far as the pore water pressure increase is, that's what we care about. So we have now at the same horizontal time axis and a factor of safety, whatever gets calculated. Can you everybody see the actual figures from back there? Yes? Okay. So the factor of safety, first, it doesn't really matter because there is no embankment. Once you start building the embankment, the factor of safety drops because the load is increasing and the pore water pressure is increasing as well. So it reaches its minimum at the end of construction. And from then onwards, the load itself doesn't change, but the pore water pressure decreases, which means that the effective stress increases. And it increases till it reaches a sort of constant value at time infinity. So from this one, we can conclude that the maximum pore water pressure, given that the load and a stress stays the same, the maximum pore water pressure corresponds to the minimum factor of safety. Okay? So this is for building up an embankment on the level ground. Everybody okay with this? So now let's look at the other situation. We are now, if the level ground is here, with the original groundwater table, now we are excavating down. We're still creating the slope, but we're now excavating downwards. Everybody okay with this? Similar process. I mean, one would think, hey, it's the same thing. But it's not. So the statement is that the long-term stability is the critical. Not the end of construction when I'm done excavating the slope. No. It is the long-term stability that's critical now. And the reason being is I'm just keeping here the pore water pressure and a factor of safety that at the original groundwater level, I'm removing the material and I'm also removing basically the saturated groundwater table gets depressed, right? I'm excavating it out. So there is a drop in the, again, pay no attention what A1 and A0 is, either one is fine. Let's go, doesn't really matter what they are. Let's go with A0. So the pore water pressure drops, the vertical line here is the end of construction. Pore water pressure drops, reaches its minimum, and then the pore water pressure eventually rebounds and raises up in a slope to maintain an equilibrium. Right? I took all the material out, so the pore water pressure actually goes back. It doesn't go back to the original level, right? But it reaches some point that it breaks out on a slope and it's drained. So I removed it, depressed it all the way to the bottom of the slope at the end of construction time, and then it recharges, finds equilibrium, and it goes back, and the pore water pressure stays constant. Okay, so for this case, there is a minimum pore water pressure. Given the stresses, given a load the same, the factor of safety is actually dropping because the pore water pressure at the end of construction starts increasing, so the factor of safety is decreasing, and it becomes constant. So for this scenario, I'm concerned about the state that's, once the slope is built and it's there. The same stuff, similar stuff, two different behaviors. So in the context of this, I would really have to be careful what assumptions I make for the material properties, right? I would have to use, say, it says the first one, phi equals 0, okay? So it has no friction, just cohesion if it's clay material. It's simply because it's in that state. End of construction, I'm going, the change allows me to use the effective cohesion and effective friction angle, but the pore water pressure is increasing. So everybody okay with these two very different states? So it's just not enough that, you have a slope, but you have to know how the slope is constructed. Because, without me telling you or at work, without having it defined how you achieve that slope, have you disturbed the groundwater table or have you embanked on top of an existing ground makes a big difference. Everybody okay with the question? No? Yes. Another situation, often you find it in dams, the rapid drawdown condition. Now, often it's defined as a sudden lowering of the water level in a reservoir. Now, the sudden should be actually in quotation marks because it's sudden relative to the permeability of the material. For example, if the water level drops 1 centimeter a day, for sands, it's pretty much nothing. So it's not really sudden. But for clays that have a really low permeability, 1 centimeter a day is still fairly sudden. But it takes, for a good dam of 10, 20, 30, 100 meter tall, it easily takes years for the groundwater or the pore water pressure to change and go back to whatever it was. So the sudden is a function, as it says, how fast in relation to the permeability of the pore solution. But let's say that we know what the material is, we know that what sudden means for that particular material. So all of a sudden, again, the same word, I'm lowering the water table. Or level in the reservoir. What's the implication of it? Let me just find some chalk and make a sketch. So, consider the situation as follows. This is the water level at the reservoir, and now there is some kind of a phreatic surface, and it looks like this. Okay? So all of a sudden, the water level goes down to that level. What happens to the phreatic surface? With time, how would the phreatic surface change? It will get lower, but slower. So the problem is that if the water level drops down much faster than the phreatic surface can change, and by saying the phreatic surface, it means that this soil is now saturated, right? However, the whatever hydrostatic pressure that was sitting on it from the water level there is now gone. So I have this region here that is saturated lower strength material, then there's nothing going to balance it because the phreatic surface will kind of change like this. Given enough time, it will be like that. So while it's changing, this material is in what condition? In what condition? Okay, so the shear strength is, yeah. So the shear strength is undrained. The lowest, whatever possible, phi equals 0. Okay, so and that's the major problem with these rapid drawdown conditions. They're leaving the slope that is experiencing this drawdown in a saturated, undrained state, and therefore the strength of the material is fairly low. So what the problem is that generally what you design for, let me just erase this for a moment, you design for a situation that you're kind of worried that this slope will fail, right? Because of the phreatic circuit, it's too high. And the other one is assumed that, well, it's going to be fine because there's this counterbalancing hydrostatic pressure sitting on it that's sort of holding it down. Think of it, failure surface soil wants to go this way, the hydrostatic forces are holding it back, right? Makes sense. But when you remove the hydrostatic forces, all of a sudden, it's gone, and now this slope can fail. So sometimes people forget to analyze the rapid drawdown condition. They assume that the water level fluctuates really slowly, or the idea of a reservoir or a dam is to keep the water level constant. And if it doesn't happen for whatever reason, well, it could be a problem. So everybody okay with the rapid drawdown condition for slopes? Earthquakes. Earthquakes are, if you will, what is an earthquake? Let me ask that question. So give me the engineering interpretation of what is an earthquake. Don't talk about damage and that kind of stuff. In its purest physical sense, what is an earthquake?
Seismic movements of tectonic plates over each other.
Yeah, it's basically you have two sides of a rock fault, something like that, and one displaces relative to the other. That's basically a release of energy, and it's dissipated via waves that it generates that travel into a medium. So what we call as earthquake is basically nothing else than a release of energy because of slippage somewhere along a fault or some boundaries. Okay, so that's what's earthquake. Now, it's not a constant force, it's a dynamic force, right? It changes with time. What kind of waves do you know that the earthquake generates? Yeah, P and S waves, right? And there's, there could be waves that basically like compression waves that travel, that the material kind of bunches up and spreads out, bunches up, right? That would be one form of wave. Another form of a wave that would be like up and down shearing. That's if I just draw blocks of material that some are going up, some are going down. So the wave travels like that way. And this could be in both directions, sideways and up and down, and there could be sort of like backward rolling motion of waves too. So there are body waves and surface waves. And generally the surface waves are the more critical, simply because all the travel on the surface and your dam is built on the surface, right? So what it's associated with is the reduction of the shear strength of the material, and I'm pretty sure I mentioned earlier that because of the moments of inertia difference between the soil solids and the water, that they start to move at a different rate and they become out of sync, and that causes forces and pushes the soil particles apart. and water has no shear strength, and hence the material loses most of its strength, if not all of it. There are various ways to go about it. The simplest one is it's kind of pseudostatic earthquake acceleration, which says to apply a fraction of the weight of the failing soil mass into the sort of outward direction of a slope, right? So if I put this long sentence into one picture, that if I have, say, a slope and I have a failure surface, and this has a weight, now part of the weight is applied as a horizontal destabilizing force. Sometimes I get asked why it's applied in that direction. Anybody? What if I apply it the other direction?
You have to assume the worst.
Yeah, if I apply it this way, then it's actually holding the slope back. So that's not really what we want. What are the values of this alpha? They're basically tabulated 6, 7, 8, 10, 12% of the weight. So 0.08, 0.06, 0.1, something like that. But this is the simplest way to deal with earthquake codes. But they work. Now on the other one, consideration of the time history of the whole seismic event can be included. That's really giving you accelerations, but then you need to do a full dynamic analysis. And that's fairly complicated. We have the issue of coupling, of deformation, pore water pressure distribution, and stresses, and a math of that one gets a little bit complicated. But it's there, people do it. So dynamic loads, Diox equation, coupling of pore water pressure and stresses. Okay, so these are the various ways to deal with earthquake loads. Stage construction, you do have to appreciate that a 100-meter tall dam does not appear overnight. Okay? It's constructed, it's built. If it's an earthen embankment dam, it's built in stages or lifts. The thickness of the stage is pretty much what one can move with an earth-moving equipment. So at any given day or any given week, it only goes up a couple of meters, depending on the site. And they break it up into sort of chunks, both cross-sectional and along the dam, simply because of the ease of constructability, of moving equipment, material, placing, this and that. So oftentimes, the good way is to simulate the same construction process by the analysis. So if I have a dam, and just sort of consider the following scenario. So I have a foundation, and I build a dam, and I build another one on top, and another one on top, till I'm done, right? So this is done in 3 stages. That's my final product is. Now, we looked at it earlier that the actual strength of the foundation is the lowest at the end of construction. So it would be possible, and sometimes it's done, that they build a stage and then they stop and wait for a couple of months. Why would they do that? Budget? Could be, but stick to the course. They run out of money. Yeah, they want the pore water pressure to dissipate. Remember going back to this figure? They're worried about the value of this. If this gets too high, that has the lowest factor of safety. So they start the next phase once the pore water pressure goes back mostly, and then they load it. So if you think of it that way, if I build it, I'm just only drawing the pore water pressure here versus time. Therefore, if this is the end of construction, and a pore water pressure would be if I build the whole thing, the pore water pressure will go up whatever to its highest. So in order to avoid that, they might build the first stage, so it might, might actually go to, say, here, and then it starts going down. I'm not saying that they have to wait till it goes back, but let's say they wait till it goes back, and then they build the second stage, that again shoots up the pore water pressure, then they wait, it goes down, and then they build another stage, and it shoots up and it goes down. So what's the problem with doing it that way?
What is the problem?
What's the problem of doing it in stages and waiting with it? Well, if I install piezometers and I measure the pore water pressure, I do know.
We're not going to get to that the maximum point of dissipation.
I don't want to get to the maximum. That's the whole thing what I'm trying to avoid.
We won't get a monolithic dam or anything like that.
There's something very practical.
It's a lengthy process.
Yeah, it takes a long time. I mean, look at it. I would have, if I built it in one shot, I would have been done here. Now it takes me, this long to build. So it takes long. But as you very well know, you can't have everything. So you never overstress the soil by increasing the pore water pressure too much. If you build a part and you let it consolidate, you build a part, consolidate, and so forth. It takes longer. So it really depends on the situation.
Can't we pre-compact site before?
Certainly, we can pre-consolidate it, pre-load it. Yeah, what's the problem with that one?
Maybe we have in such kind of region, it's not easy to compact the soil.
How do you compact the soil?
There's so many compaction equipment, it depends on the type of soil.
We're talking about saturated clay. How do you compact saturated? How do you compact saturated clay?
Cheap rollers.
You can't. Yeah. And all that takes time. So if you have access to the site tomorrow and you spend a year dewatering or something with saturated clay, dewatering it will take time. So start construction later. If you start with a smaller one and you wait after the first level, you still wait. So it takes time. So why cannot we compact saturated clay with a shipfoot's roller? Yeah. Rule number one of consolidation. When you apply that roller instantaneously, what's taking the load? The water. The soil does not consolidate. You're just basically shoving the mud and doesn't do too much. You're pushing the water. Okay? So still, if I go and have access to the site and I dewater it or some other means of trying to reduce the water, it still takes time. So that's the key thing. Okay. Other situations, surcharge loading. When you look at the slope stability, you can add extra load, whatever surcharge would be. So that would be an issue that you need to consider of not just the slope itself, but what other loads will be applied on the slope also. Okay. Submergence of the slopes. Some slopes are underwater. Be that this rapid drawdown condition. So remember that the slope is actually subjected to hydrostatic pressure. And also there are completely underwater slopes in rivers, lakes, oceans, whatever. So that poses a set of challenges. Now, in addition to that, we can try to reinforce the slope. I believe there will be a few topics about that for the project. So we can help the slope by soil nailing and all sorts of other means of slope stabilization. Okay, so these are all situations that you have to consider in a life of a slope that you're trying to analyze for stability. Sometimes it's a combination of events. You can have a rapid drawdown and an earthquake. Sometimes, unlikely, but there's a potential. So, a combination of events. Now, how do slope failures look like? I'm going to try to zoom into the figure. So we'll go from one to another. Clay slopes. We can have, and when you think of slope instability, oftentimes you look at a figure and it's kind of like a part of a circle or something like that. And some soils do fail like that. So when we're going to talk about the slope stability methods, we differentiate them between circular and non-circular methods. And circular are the simplest. And it comes from the shape of the failure surface, that it is part of a circle. So that would be a rotational slide. It's a sort of rotation of a mass of a soil along a circle, which is a special case of an arc. We can have a shallow one. It's basically a slipping layer of soil that's kind of slipping down. And we can have these non-circular, that the failure surface itself is not part of or part of it is a circle, but part of it is some other function, either a line, or arc, or whatever else. So it would be a non-circular. Compound slides, we have now basically part of it is sliding on a harder stratum at the bottom. And so you have a part of a circle here till it hits the harder stratum, slides along, and then comes up at the top. Okay, so it would be a sort of non-circular but a well-defined region of it of why it's non-circular. Everybody okay with this? Translational slides, basically you have a large block of rock that's for whatever reason sliding down. So it's kind of sort of, I don't know, maybe not, slope failure. And similarly, you have a large mass, it has a beginning and it has an end, but generally a continuous cross-section, like a slice that's sliding down. And these would be the so-called infinite slopes, and that's sort of the first topic that we'll look at when it comes to slope stability methods. And then flows. They are slope instabilities, but the material is not really like a one solid block or multiple blocks, but rather more like a fluid. It kind of flows down, mud flows. There are various kinds. And then sort of the simple ones. Now the more complex one, it is basically what we perceive as slope instability is a set of failures. Right? You can think of it as kind of like a domino effect. The first one fails at the top, it adds extra load to the soil region lower downslope of it. So the extra load fails that one and it slides down. So there are kind of successive slips down the slope. Special kind is this retrogressive slides. That one part, it's a circular one, generally on a harder stratum, that removes the material that holds back the next set, and that fails, and finally that fails, and the reason it's called retrogressive, because it moves backwards, right? It kind of moves in the opposite direction. Okay, fairly complicated. Slump earth flow, very similar to this one here, depending on type, and these are kind of more like at a borderline of mud flows or debris flows that we're not really concerned with. So this course is mainly these. circular, non-circular. You're going to look at rock slopes. And that's pretty much it. The rest are either a combination of some of them or really can be better addressed by fluid mechanics than solid mechanics. If there are mud flows or debris flows. So any thoughts, any questions about the types of slope instabilities? Nope. So if there are no questions, then might as well look at slope stability. So a few historical notes of how slope stability was developed. So this old guy Coulomb, he made a lot of contributions. So he's famous for, at least in solid and soil mechanics, for friction. So the more Coulomb failure surface is like cohesive frictional material. So Coulomb is the frictional part, Coulomb friction. So he looked at it, looked at the stability of retaining walls, and he figured out that if I have a retaining wall, and in a fairly generic sense, I would have the following situation. That if there is a retaining wall, there would be some kind of a failure surface where this weight of a material would kind of slide out along a failure plane. And he said that, well, this material is held up by basically the friction along the failure plane. Sort of, makes sense. However, this Coulomb method applies to what kind of a soil? The frictional stuff. Yeah, sands, granular materials, purely frictional materials. Okay, so anything that failed in clay, Coulomb and his theory just did not apply. So 50-some, 60, 70 years later, people started noticing that if I have a clay slope, then the actual failure occurs along a curved or circular, but not a straight line, not a planar failure surface. So this doesn't apply to that. And it took again another, 70 years or so that there would be actual methods postulated based on simple statics, if you will. So if you go back to the factor of safety equation, that says capacity divided by demand. So if you look at in this relationship to that, what is the capacity? Of course. So if I now look at whatever normal force, so if again, the angles doesn't matter. So if I have this normal force M, so that would be the frictional force, let's say T would be the normal force times whatever friction angle of the interface. And this basically acts on a slice that in a 2D is a 1 meter thick strip of material, right? So if I know the length, I would be able to sort of calculate that right away. So it's very simple steps. Everybody with me? The other one, if I look at the equation here in the same context, that would be the weight. What is now the capacity? Is it any different than that one? Its form? No, it's it's the same stuff. It's the shear strength. I'm not using the form yet, but now this is a cohesive material. See? So Not a frictional, but a cohesive material. And the demand is the same for both. That's the weight of the failing solid mass. Now, there is a huge problem that separates this from that. We need to find the failure surface. So for this Coulomb case, the failure surface always started at the base of this retaining wall, and with some angle, call it, let's call it alpha, some angle it went up. So if you knew this angle, and you knew obviously the height of the retaining wall, you can always calculate the length of the failure surface. Whereas for a simple clay slope, let me erase this. What is the factor of safety? In order to have the factor of safety, you need the demand and a capacity. Both for the demand and a capacity, you need weights of some volume of soil material, and you need a failure surface on which you calculate the shear strength or the shear forces. But generally, if I give you a slope, what is the huge question? Think of it what I just said for the one up there.
To define our failure slope.
Exactly. The actual failure surface on which the soil fails, who knows? It's not defined.
Predict.
What do you mean? Predict or protect?
Predicting like where is.
So we have now, and for most slopes, other than the simplest ones, we have two questions. What is the factor of safety, and where is the failure surface? So I'm just going to write failure surface. You have to know both. And how many failure surfaces there could be. Potentially. Yeah, infinite number of failure surfaces, and each has its own factor of safety. I want the one that has the lowest factor of safety. So when we talk about, and you know, for these methods, we'll talk about it later much more in a course, but you know, all of these methods will give you the factor of safety, whatever the method is, for a given failure surface. Just the problem is that there could be an infinite number of failure surfaces, so it's not only enough or not enough to calculate the factor of safety, but you got to know where the minimum factor of safety is. So oftentimes the problem becomes fairly complicated. How do I find the factor or the lowest factor of safety and the associated failure surface? And that can be complicated. So programs deal with it various ways. We'll look at it later in the course, but I'm just trying to sort of tell you that if you have a well-defined failure surface, you calculate its factor of safety. But for a given slope, there is no little sign that somebody put in the slope saying that the factor of safety is, it's down, or the failure surface is down there. Nobody knows. It's part of the analysis to find it. But going back to the 20s, 100 years ago or so, people started to realize that things get a little bit more complicated. But even this one, if you look at it for historic purposes, the sketch of slope stability analysis, it is based on nothing but first year undergraduate statics. That's pretty much it. So let's look at it. So this is a harbor structure. So we have some kind of a surcharge sitting. There's a vertical wall, and this is this is where the ship's from. That's the water level. So the failure surface is basically a line, horizontal part, and one going up. So how did they calculate it? Well, they broke it into couple of components. He broke it into one triangle, a rectangle, another rectangle, and another little triangle. So what he did is that he calculated the weight of an area of a triangle times 1 meter thickness times unit weight of the soil. This is unsaturated and saturated is below the water level. For all of them, he was able to calculate the weights of them, and then he started to draw these force polygons, basically a vector addition on a piece of paper, and he did this iteratively till all the forces basically closed up. And based on that, whatever the ratio was of these forces on these blocks, he was able to calculate how much under or over the forces were. So he had like the last leg of the vector was missing, so whatever force was needed there, its magnitude was basically how much extra capacity there was in a system. So first year static, vector addition. Right now, if you look at it, it looks kind of simplistic, but at the time that was the state of the art. And similarly, a few years later, for a different structure, for a river kind of wharf and everything, much bigger failure surface. Note this one is a line, a different line, another line. So it's kind of 3 lines, nothing complicated. That one, on the other hand, it is now a sort of circular, or well, not really, but kind of arced failure surface. But if you look really carefully, it's pretty much the same as the previous one, because what the fellow did 103 years ago, that he cut this into triangles and trapezoids. He calculated the weights of each of these. He took moments and so forth, and he still plotted this vector diagram and tried to close it. So basically, that's the solution, and these are drawn to scale, right? So magnitude-wise. So complicated, tedious process. It tells you very little about the actual soil mechanics aspect of things, of what is actually happening to the material. And I guess by now everybody understands it, that there is yield, there is plastic deformation along the failure surface, and that's, an order of a magnitude more complicated than simple statics. Yet, up until 20, 25 years ago, almost exclusively, even the best methods that we will cover in a course are based on this limit equilibrium that I talked about last week. So limit equilibrium, recall it, it is nothing but a limit equilibrium of demand and capacity with some assumptions. So other than the shear strength of the soil, the rest is pretty much statics, taking moments, adding forces, and so forth. And interesting, I believe I mentioned it, that even these days, the majority of consulting engineering offices, when they do slope stability analysis, they use limit equilibrium methods because that's what the people are familiar with, that's what they have experience with. But now finite elements are kind of going more into the practical applications, into design and analysis, simply because they can do so much more than what limit equilibrium can do. Okay? So any questions about this sort of historic background of slope stability? And let's look at another one. I just put this up for the fun's sake, that I have now a clay slope, below water table in a harbor structure, and the fellow 101 years ago realized that I don't even know where the failure surface is. So he plotted up a bunch of them, or rather calculated a bunch of them, and started to plot it up and kind of map out where the minimum would be. So we'll look at it later in the course, but how do you deal with, and let me just erase it for the fun's sake and redraw it. And I want you to think about it for a few moments without knowing too much about it. So, what is the factor of safety and what is the, let's call it, failure surface? How would you find it? So give it a moment and think about it and come up with interesting ways of how would you find, and we'll talk about it later in the course towards the end, but I just want to see, you're an engineer, 100 years ago, you're faced with a problem, there is a clay slope, you know that the failure surface is circular, you just don't know where it is, and you don't know what the factor of safety for it is. Give it a thought. Anybody? Any ideas?
We can check with the water pressure, like what table is.
Let's say it doesn't matter. Let's say there's no water table. It's just clay. No water table. We make life simple. It's a homogeneous, moist clay. There's no water table. I just want you to think about it. How would you find the failure surface that has the minimum factor of safety?
The failure surface is where the factor of safety is equal to 1.
Factor of safety could be less than 1, right? Yeah. So I want the minimum
Iteration.
of
Say yes first failure surface 1 meter away from the edge, and then you calculate factor of safety equal to the same for 2 meters, 3 meters, and then
okay, guessing. So you randomly assume a failure surface. Now, I gave you a hint that it's a circular failure surface. So what defines a circle? Center, xy coordinate, and its radius, right? So 3 parameters define a circle, right? So I can randomly select centers of a circle, see if it intersects the slope. I'll pick a point here, and I pick a radius of whatever it is, so I can draw a circle, calculate it. Pick another radius from that point, and calculate it. I can pick another point, and I can have pretty much an infinite number of possibilities, right? So that would be the brute force, throw a dart, see what happens. Probably you need quite a few numbers, but eventually you would have a good feel of what is the factor of safety variation. Okay, can we do better than this? Okay, how?
Determine the critical height. Determine the critical height.
I know what the height is. Height is h. I know everything about the slope. I know its slope angle. I know its height. I just want to know what the minimum factor of safety is, then associated failure surface.
practical test.
Oh, so like a 10-meter tall slope, bring up cars and cars of load, pile it on top till it fails.
Will you get the fuel always fuel?
Okay, lab testing in a centrifuge perhaps. Yeah, I can do it, but I'm interested in calculating.
More
More circle. What you want to do with more circle? Yeah, the question is, where is the failure surface that has the smallest factor of safety? We looked at young ladies, dart throwing approach, pick a center at random, pick a radius at random, calculate it. If you do enough of them, eventually you will get close enough. Come on, guys. Expecting all sorts of good ideas. I know it's the afternoon, but so let's try to improve on Earth's suggestion. How can we improve on? You ever thought?
then you can make a grid
Yeah.
to have like
Instead of doing it randomly, let's do it in a sort of more organized fashion. In a more organized fashion would be, I select a bunch of points. I'm just going to draw a few. So at each of these centers or intersections, that would be the center of the circle. For each of these points, I select a bunch of radii and I calculate those. Okay, so maybe I have this really coarse grid of 1, 2, 3, 4, 5, 25 centers, and for each center I select maybe 25 radii. Okay, everybody with me? So let's say at this point, I calculate 25 factors of safety, I keep the minimum, and I keep the failure surface that resulted in a minimum. Then I move on to the next one and I repeat it and I repeat it. And eventually I will have 25 volumes of factors of safety, and from that one I can find where the minimum is, I can interpolate in between and so forth. Okay, that's quite a few programs even these days do it that way. Instead of having a huge number randomly distributed centers and radii, I do it in a more orderly fashion. Okay. Anybody else? Any other thoughts? We ultimately think of this, try to think of this problem from a different perspective, from a sense of I'm trying to find a minimum factor of safety of a problem posed in this case for a circle that's simple with 3 variables, given everything else constant. What was the key word in this sentence that I said? Who was murmuring something that started with an M? Yeah, minimum. So, all of you struggled through undergraduate. At some point, you took a math course or something that had an issues of minimizing functions, right? Yes, no? Yeah, I know. Brings back bad memories. So, you can look at this as finding of a minima of a function in a 3-dimensional space where one of the dimensions is the x-coordinate, another dimension is the y-coordinate, and a third dimension is the radius of the circle. You're taking a computer apart, or what you do?
No, it's a screen that I used to draw. I'm trying to plot what you were explaining.
Okay. Okay. I thought there's another part to it somewhere, it's in pieces.
Oh no, the iPad was dead.
It's kind of unnerving to see somebody draw on a piece of iPad screen. Okay. So, it is finding a minima of a function. Now, the problem with that one is that, like any function, I'm just drawing a simple one. This is the function. Basically, it's a one variable function. How many minima are there? And which one I want? Yeah, I want like this is a minimum, that's a minimum, this is one, that's one, this one. I want the global minimum. Over its range, I want the lowest minimum. Okay? Now think of this that instead of this is 1D, so on 2D, in 3D, these are basically surfaces in space. The x, y, and r. Center, 2 coordinates, and a radius. Okay? So you can look at the problem of finding a 3-variable function's global minimum. And there are a whole set of mathematical methods of doing it. The simplex method, for example, that's the simplest almost. Very well established mathematical base. I don't need to throw it at random. I don't need to have grids. I just look at it from a purely mathematical perspective that I'm minimizing, in that case, a 3-variable function. And that will give me, given a good method, that will give me the factor of safety and the associated failure surface that corresponds to the minimum. Okay, so that's a completely different way to look at it. And imagine a situation, what I did for my masters, that I had rock slopes with multiple kind of non-circular failure surfaces, so the thing looked like, let me show you how. So it had like these sort of facets. So each of those could be like triangles or whatever polygons. So each of these had like the coordinate of this, so there were 2 unknowns plus the inclination of this face. Actually, no, just the 2 coordinates there, the 2 coordinates here, plus the angle of that side, 2 coordinates plus 1, the xy of this plus the angle, 2 coordinates plus 1, 2 plus 1, and the last one is 2 plus 1. So we have 3, 6, 9, 12, 15, 17. So in order to find the location of the minimum factor of safety and a corresponding failure surface, I have to find a minima, a global minima of a function in a 17-dimensional space, in a simplest case. And if I have multiple wedges like this, then up to 30, 40-dimensional space, you have to find the function's global minimum. I mean, in a 3D space where x, y, and the radius, you can kind of imagine it how it looks like. It's some kind of a surface that has a value. But in a 17-dimensional space, you can't even figure out what I'm doing. Okay? So I'm just trying to illustrate this at this point, and of course, that the big question is not only to find the factor of safety, which we'll look at various methods, but it comes the issue of where is the factor of safety minimum for what failure surface. Okay, so when you press that button on a computer and the software runs for 2 seconds, it does a lot of things behind the scenes. If you were to do it by yourself, it will probably take you equivalent to probably months of work, with ample opportunity to screw something up, as far as calculation goes in Excel. It's good. Okay? So let's take a break and then we'll look at the simple stuff. Pretty lousy. So, I had this question of just clarifying of what's on the midterm as far as sets of slides go. So, soil mechanics review, the 00 underscore soil mechanics. I already bothered you with that one. I tested you. I understand that you know everything there is to know. So I'm not going to ask that again. So set with 01 called earth structures and types applications. Yes, all of it. 02 selection, design, and construction. Yes. And number 4, monitoring dams and slopes. So 1, 2, and 4. Clear? Everybody? Clear? Yeah. Good. Excellent. So we'll save 3, 5, and 6 for the second one. Any more questions regarding the midterm? Other than what's on it, which I just said. 1, 2, and 4. Anything and everything goes. So we're good? So we're going to start with the most simplest stability issue, something called infinite slopes. So my big question to you is, what are infinite slopes? Are there actually infinite slopes? And if there are, how do they look like? After infinite. So let's put this question, think about it. All right, you're ready. Infinite slopes. How does an infinite slope look like? What do you mean by a line? It's an infinite slope. It has no beginning and no end. So if I sort of think back of it, let me draw this slope in a failure angle. Is this an infinite slope or a finite? Yeah. It has a bottom, it has a top, and it's a failure surface. Now, if the failure surface happens to be something like this, and my only concern that the thickness of this h and a slope height, capital H, that capital H is much, much bigger than the thickness of the failing mass, then would that be an infinite slope?
Yes.
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 How realistic are they? My question to you is infinite slopes. Yes, no, maybe. They're not. They're not. Okay, let's go back to this set of slides. Not here. Other set. Hey, any of these failure mechanisms look like an infinite slope? So you like the ghosts moving the cursor of the mouse somewhere up here, there. So a shallow one would be a slab slide or something like that, where the thickness of the failing mass is much, much less than the actual slope height, can be characterized as infinite slopes if we neglect the sort of the toe and a crest area, or the bottom or the top of it. Okay? They're really, really an idealization of a slope failure, but yet from the perspective of sort of mathematics, of formulating, there's sort of the kindergarten level of the formulation. And the funny thing is that if you understand the steps, not the equations more so, but the actual steps of the equation of how it's formulated, you will be able to understand much easier the complicated methods, because they go through exactly the same steps, but their assumptions are different. So let's look at the infinite slope. So as the clue here was, it's useful for landslides. So you have a large sliding mass of relatively small thickness in compared to the actual height of a slope. Soil properties, we go simple, one soil type, effective friction angle, cohesion, and the unit weight of the soil. Now, the funny thing with this one is a huge assumption, and I'm just going to draw what's shown there a little bit more. So I have this constant thickness tract, and it is subdivided into basically, look at it, these are the slices, right? They're blocks of soil. And there is an infinite number that way, and there is an infinite number of these blocks the other way. Okay? So in that case, if I isolate only one of them, there is always one next to it on either side. Okay? So any force that's applied by this one onto the next one is balanced by the force from the next one onto this one, and same the other way around if there is another one. Okay? So there is one block always on both sides, like the infinite. Everybody okay with this assumption? So then a weight of a slice, knowing what its horizontal width is, and knowing what its basically thickness is, see, again measured in the horizontal direction, in the vertical direction, I can calculate that the weight of the slice is basically the area of the slice times gamma. So there are two things to notice right away when I'm setting up this equation. There are two things that are not obvious. One of them is pure geometry, another one of it is a huge assumption. So who can tell me the geometry behind that equation? Sometimes it puzzles students for days. And what is the huge assumption that I'm making? Look at the quantities, look at the units, look at everything. So spend a moment. It is fundamental, the big assumption for you to realize on your own, other than me just telling you. Because at later derivations, it's not mentioned at all. Well, I'm not going to mention, I assume. And I'm assuming that you know. Look at that simple 4-component equation and make sure you understand how it's there. Okay, so remember what she said. It must be some good stuff.
Not really, but
Oh, okay. But you need to say something smart, so it must be
blame it on the distance.
So let's just concentrate on finding the area of the parallelogram. Why is it z times b? Where z is a vertical distance, b is a horizontal distance. It's a simple geometry, but sometimes it trips students over that they're lost.
B equals to L cosine beta. And because
Where is, okay, I'll see you now. You're on the right track, but you're overcomplicating your life. So let me draw this stuff again. You're right, but so my question to you is that you redraw it here. Let's make sure I sketch the right stuff. Where this is C and that is B. What's the area of that one? Okay, everybody knows why.
yes, because it's a rectangular.
Yeah, well, basically the simplest one, you cut off this triangle, you put it there, and it's a rectangle of C times B. A number of times I asked it over the years in the midterm or something like that to derive it, and a number of students kind of froze. They had no clue what's going on. Okay, so that's number one. Everybody clear how I got C times B? Good. So let's go back to the major assumption that she said. Are the units consistent in deriving the equation? Let's go one by one. What's the unit of weight? Well, it's newtons, whatever.
Yeah, everything is pretty in depth. Like you're multiplying by 1 meter every time.
Yeah. So this should be, newtons, right? What's the unit of unit weight? Yeah, newtons, kilonewtons, whatever, per cubic meter. What's the unit of this? So we're missing one dimension, right? This is a 2D problem. The weight is actually derived from the volume times the unit weight. Unit weight is in cubic meters. So we're missing a dimension.
That's the thickness and we are assuming it's a unit.
Yes, so this is a huge assumption that oftentimes not spelled out and makes some students confused when they have to do it on their own, that it is assumed for 2D problems there is a 1 meter unit thickness. So it is a 3D problem in essence of a slice of a unit meter thickness. And I'd say 11 out of 10 cases it's not spelled out. Right? You have to assume it. And the assumption is, if you read a book, if you look at these formulas, the assumption is basically on you to know this. So I want you to be absolutely clear that there's a unit missing in this equation. This is times 1 meter, which is the thickness. Okay? And many more later on, I'm not even going to bother to mention it. If something is missing, it's basically up to you to figure out the derivation that there is a unit implied of thickness. So everybody absolutely crystal clear? Good. So that's the weight of the slice. Now, the pore water pressure at the base of the slice, where the slip surface is, and the slip surface is inclined with angle beta from the horizontal, is unit weight of water times the height of the water. Whatever it is, if I stick a piezometer at the center point of the base, the water will rise, whatever this HW height. It may be fully saturated, it may be completely dry. Doesn't matter. Water level is gamma water times HW. Okay? In order to model all the slices downhill and all the slices or blocks, whatever, uphill, we have these forces of QR and QL. So Q left and Q right. These basically cancel, right? There's an infinite number to the left, there's an infinite number to the right. So any questions? I want to really go slow on this method. Some of you seen it, I teach it in some form in my undergraduate soil mechanics, in the introduction of slope stability. The key is if you understand what's going on and how things are, later on all the other methods built on the mechanics as far as putting it together of the simple method. So let's go to the next one. So it's an infinite slope, Q left is equal to Q right. So that gets rid of forces on either side, so you can look at a block of soil in isolation. If I can find the factor of safety of this block of soil slipping downhill, that would be equivalent of finding the factor of safety for the whole slope. Because Q left is equal to Q right, because there's an infinite number on either side. So it's a huge assumption. Now, I want ultimately to find what I'm looking for. I want all the forces that are trying to fail this block of soil, all the forces downhill, this would be the demand, all the forces on the slip surface holding it back from sliding down, this is the capacity. So I want whatever this is divided by that. That gives me the factor of safety. Again, the fundamental definition of what factor of safety is. That's all that I want. So now our job is to find the component, and so far what we have only is this. We have the weight of the water coming down, plus we have at this point the pore water pressure, whatever is under. Draw another arrow that's fixed. So these are the two forces that I have, both of them acting down, and we assume that they are acting through the center of this base. Okay. Since I know the width of the block and I know the angle beta, I can calculate it of what he started to say there. I can calculate L, which is nothing but the interfacial area between the block of soil and the whatever is underneath it that remains stationary. Okay? So, in order to find all the forces that are perpendicular this sign and parallel to the base, I can do this. So let's call the one that's perpendicular P, and let's call the one that's parallel T. So if I go back here, P is normal or perpendicular to the base, T is along the base. So if I know W cosine beta is equal to P as a force, W sine theta is equal to the one that's parallel to the base. Why can I do that? Well, if I look at it just the base, if I have W going this way, I know this angle is beta, so it's not this, so it's that angle, so I'm breaking it down. If this is W, I'm looking for this component, and I'm looking for, I guess, that component. I know the angles, probably third week of undergraduate statics. Now, what does the perpendicular force do? Think of Moore Coulomb equation. It is the what kind of stress? Yeah, it is the normal stress, sigma. What is T? Yeah, it is the shear stress. I need to stress out at this point, that's why I'm stressing, you have to distinguish between stresses and strength. They're two different things. Both are pressures. One is stress, one is strength. So stresses are the what? Demand or capacity? Stresses are the demand. Strength is the capacity. So right now we are finding the normal stress and the shear stress times L. Look at this equation, sigma times L or tau times L. Is it complete or is there something missing? Yeah. Remember, what is the fundamental definition of pressure? It is force over an area. So I have a force, I have pressure, and I have a length. So what's missing? Yeah, the thickness, right? This force is basically acting on an area that's into or outside of the board. I'm going to draw it dash. It's basically acting on a rectangle that's coming out of the board, and it's 1 meter thickness. So here too, I did not put that there. So it's understood that times 1 meter to get the units right. So if I now rearrange this equation, I would be able to find what the normal stress is from that equation and what the shear stress is. And plane geometry, as he said, I can know what B is from L and vice versa. Okay, so this is the stress. This is the driving. Now, the strength of the interface of the soil on the block that's moving and the one that's not moving underneath at that interface through the soil is assumed to be a more Coulomb material. And I'm just repeating the more Coulomb failure criteria for shear strength is the strength is equals to cohesion plus effective stress times effect 10 of the effective friction. And, okay, nothing new. Now, let's introduce the concept of the mobilized shear strength. It is the available shear strength divided by the factor of safety. This is, again, remember, this is the amount of the capacity I take out that can counter the demand. So if the demand is equal to the capacity, then the capacity is fully mobilized. If the demand is less than the capacity, then I'm not mobilizing full shear strength. If the demand is greater than the capacity, well, I guess the slope is toast. Okay? So the factor of safety is a measure of how much of the demand I'm mobilizing. You good? Now, from basic statics, we know that this system should be in equilibrium. So, on the left side, I have the demand. On the right side, I have the capacity in its fundamental form. Right? This left side is basically whatever here. The right side is 1 over Fs times the shear strength. It's basically this equation, but I made a substitution that for sigma, I substituted this. And for pore water pressure, I substituted that. Actually, I didn't, but it doesn't matter. You can substitute it. So this is now the equilibrium condition. It is assumed that in equilibrium, in this limiting equilibrium. So when I know my job is to find this factor of how much the factor of safety is mobile, so how much the a capacity is mobilized, I solve for the factor of safety, and there you have it. If I know the dimensions of this basically the block, the thickness of down to the failure surface and so forth, and you see that the actual dimension of the block B, it disappears. It doesn't matter. You see? Only the thickness to the failure surface Z is important. The rest are basically. So that's the derivation of the simplest slope stability problem of an infinite slope. It's very, 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 very slow and fairly detailed. So let me ask it again. Any questions? Anything that we need to repeat? Now is the good time, because if something is not clear, anything that comes later will be even for cloudy and rainy and snowy and all kinds of stuff. So we're good? Okay, let's do another one. Now, there is now steady state seepage occurring. So we have the same setup of the problem, but now there is a downhill flow of water. In the previous case, we said that there is water, but it's just sitting there. Now we have downhill movement of water. And that is, if the case of steady state seepage, I would be able to find what is the height of water at any point, wherever I want, along the base or anywhere else, with this little equation. Since it's fairly simple, this is kind of your homework for you alone at home when you're bored in the middle of the night to prove that equation from fundamental principles. Okay? It's fairly simple. So I can now calculate what is the actual situation. Now, for a purely frictional material, and the water table is at such location that it's at the ground surface, the factor of safety equation simplifies to something like this. And anybody sort of remembers from soil mechanics what that is? Effective unit weight. Inverse, but anyway, effective unit weight. So, if for a simple situation like that, okay, I'm not showing the full factor of safety. It is just like the other one. I want you to think about it and go back as an exercise and derive it if you want to, the full equation. It is basically, I gave you, instead of HW here being a volume like that, now HW is a little bit more complicated. So you can plug this one into there to get pore water pressure, and then you can carry on the same steps to put pore water pressure here, and you would have an equation for the factor of safety of an infinite slope with a steady state downward seepage. Simple steps. Okay, so that's sort of homework in a sense that I'm not going to collect it, I'm not going to look at it, it's just for you to convince yourself that you understand the previous method's derivation. Derive it and see. Because ultimately, I hate to tell you, the second midterm will involve a lot of these derivations of stuff and understanding of what's going on. And it starts simple and gets more complicated. Okay. So let's look at now at something else. The phi equals 0 method. First and foremost, what is the phi equals 0 condition? So soil mechanics. But there's more to the story. What's the other name of the phi equals 0 condition?
Angle of error is 0.
Yeah, but why? That's the big question.
Undrained.
Exactly. It's called the undrained condition. Right? So it is when the pore water pressure is such that it cannot dissipate in clay, just like he said. So we cannot rely on any frictional strength. It's purely the cohesion that's giving the shear strength. So our tau is equal to Cu. So based on that assumption, I'm just going to zoom back to a set of slides, if you remember it from earlier. We saw on one of them, so just putting it in perspective. So who can find it on this slide and tell me why it's there?
You have it on the bottom chart.
Yep.
At the
It says the phi equals 0 method applicable in this range while I'm constructing it. So why it's there and what does it mean?
well, you're applying the load, so technically the pore water pressure out of the tank dissipates, or you're under undrained conditions.
Okay, so using the phi equals 0 method is applicable in a scenario where I'm just loading that saturated clay rapidly. It has no chance whatsoever to dissipate. It's in an undrained conditions. Therefore, its strength is purely whatever cohesion is, a Cu is giving you, and it's in this phi equals 0. So in that case, your analysis method is going to be based on this phi equals 0 condition, undrained shear strength. Okay, so enough of soil mechanics for that, and let's go back here. So for the soils under such condition of no drainage, they experience a failure surface that takes a shape of a circular arc. So these are saturated clay materials. So it is now assumed, is it true or not in reality, who knows? The method itself, and this is what we will see, and something very important that when you're studying for the second midterm, you got to know what the assumptions of each method are and why are they there. Because that's giving you the method's strengths and weaknesses. So this method assumes that it's a circular arc, and it assumes that the rotation of a rigid block of soil along a cylindrical failure surface in 3D. So carefully now, what does it mean? Rotation of a rigid block of soil. Okay, not deforming where? Okay, a rigid block of soil. Not deforming is right, but where there is no deformation. Okay, let me draw it. I'm going to draw it in 3D. So first, everybody sees that it's a cylindrical failure surface, that basically this is the cylinder, like in 3D. So that's the cylindrical part. Everybody sees that? Why it says cylindrical? Good. Because then I'll erase this line because we don't need it. It just confuses the heck out of us. Now, what about the assumption of a rigid block? Okay, so what it says that if this fails, it would look like something like this. Inside the soil, other than at the failure surface at the edges, right? Inside the soil block, there is no deformation whatsoever. It's a rigid block. The only deformation is that, well, it slides as a rigid block and this stuff stays the same. Now, for real soils, real failure surfaces, let's go back to here, to the other set of slides, and let's look at some. How realistic is that the failing soil interior to it does not deform with just one big block of soil? Not at all. Okay, so this is a huge shortcoming, this assumption that it does not reflect realistic soil behavior of a rigid soil mass. Inside, there are deformations within the soil mass. So, and to contrast that now to what the phi equals 0 method says, later on, when we look at the methods that they actually assume, let's say Bishop's method, it doesn't tell you too much at this point, but there are methods that subdivide now the whole mass into these slices, and they say that within each slice, it's a rigid block, but the slices can move with respect to each other, so there will be deformation between the slices, not inside the slices, but between the slices, okay? So to overcome the shortcoming of one rigid block is now, let's make a bunch of rigid blocks, as many as I want, and these would be able to, so when let's say this one fails, it would look something like this. Something like this. So each block can individually move and there's deformation between them. So everybody clear with rigid blocks, cylindrical surface? Now, on the failure surface, undrained shear strength, Cu, is mobilized. This is coming from the assumption, right? No drainage. The strength of the material of the saturated clay is only Cu, the unconfined, sort of compressive. Well, unconfined cohesion. So the undrained condition represents the end of construction, short-term stability. So when you're faced with a problem of analyzing an embankment, then your first point is, okay, at the end of construction, I need to see if it's stable, how stable it is, and so forth. And let me flip back again to the other set of slides that we talked about. Right, this set of slides, factor of safety, there are different conditions, right? These various, this last column, different factors of safety. So you have to find at the end of construction, what is the appropriate, say, let me go to this one, greater than 1.3 for end of construction with no reservoir loading and undissipated foundation for water pressure. So if you use a phi equals 0 method for this earthen embankment slope, then you know it has to be greater than 1.3. We good? Okay, so now we know everything about the assumptions of the method, what it does, what are the limitations, right? How realistic it is, and so forth. So let's look at the actual setup of what we have. We have now the weight of the slope, which is basically the area of this that I'm tracing out with the cursor. Hope you can see it, right? So the area of this multiplied by 1 meter multiplied by the unit weight of soil. Now, note number 1. How do we calculate the area of this shape? That's issue number 1. If you're faced with putting numbers on it and calculating the factor of safety. Let's say you're writing a program. Yeah, but you're writing a program to calculate it. Computers are pretty dumb. If you tell them to open a door, they would never do it. Unless you program them how to do it. Right? So, how do we find an area of a polygon? Yeah, simplest one, let's not complicate life too much. Cut it up into a bunch of triangles, find the area of each triangle and add it up. But there are algorithms for areas of polygons and so forth, but that's beyond the course. So the first problem is that, well, it's a complicated shape. We have to find the area so we can multiply it by the unit weight of soil. Complication number 2, right now it shows just one soil. What if there are multiple types of soils and you know where the location of the boundary between them is? Well, that makes life a little bit more complicated because you have much more complicated polygons that you just sort of redraw this and practically make situation worse. So this is how the slope looks like, and make it simple. This is soil 1, this is soil 2. That's my failure surface. So now I have to find the area of this polygon, and I have to find the area of that polygon. If I have different kinds of soils, then you have all sorts of interesting looking polygons. But let's assume everybody knows how to cut it up into triangles somehow with scissors, X-Acto knife, whatever. Measure the area of the triangle, and there you have it. I'm just trying to illustrate to you that very easily it gets complicated if I ask you something like this on a second midterm. I don't feel in a good mood, I want to fail everybody, so let's put something like this. And, just trying to put it in context that even in a simple case, stuff like that, finding the weight can get pretty complicated. So, if I know how to find the weight, that's bearing vertically down. So at any given point, I would be able to find a component of that weight via very similar techniques what we went through here to find at any given point the perpendicular and a parallel forces. I'm not even showing it because there is a reason for it. So this is part of it is a driving force is the weight. The failure surface itself is assumed to be at an arbitrary location, as discussed earlier, centered at point O, so the xy coordinates are here, and it has a radius r. It is at a distance x horizontally from point O. The angle that's subtended by the crest intersection and the toe intersection is theta. And we have whatever the capacity is, the shear force, which is the shear stress or a shear strength rather, over the length of this arc, which is easily finded by the radius times the angle, subtended angle, right? So now comes the next set of assumptions for the method. We go one by one. Soil properties, Cu and gamma. The length of the failure surface, L times R. There is one issue right there where the cursor was. How do we measure theta? Oh yes, in radians. If you measure it in degrees, well, you'll be in for surprise. Right? So you have to measure it in radians. Like now, the average shear stress on a base is whatever the shear force is divided by the length, right? So one big assumption is that this average shear stress is you're using it as a uniform value along the failure surface, which is may or may not be true. If you think of it that way, one would think that the stresses close to the ground surface here are less than somewhere deep there, and also here close to the ground surface, the stresses are, different. So the big assumption of the method is that I'm using the average shear stress, which is not entirely true. So, a huge assumption of the method is that it is based on moment equilibrium. So we can have, these are 2D problems. What kind of an equilibrium can we have for 2D? We can have moment and two equilibriums, one in horizontal forces and the other one the vertical forces. So we can have three conditions of equilibrium in 2D. Sum of forces in a horizontal direction equals to 0, sum of forces in a vertical direction equals to 0, and some of the moments that are basically sort of out of plane. Okay? So these are three conditions of equilibrium. Now, when we have these slices, then we can have three conditions of equilibrium for each slice, and like a local condition of equilibrium. For each slice, the two force equilibriums and a moment equilibrium. And we have another set of equations that's for the whole system, like a global set of force and moment equilibriums. But for this method, rigid block, we have only the three global equilibrium conditions. Now, the phi equals 0 method says only that there is a moment equilibrium. It does not claim any force equilibrium. So you see a huge shortcoming right there. It says only that the equilibrium of moments is basically maintained. It says absolutely nothing so far about force equilibrium. So the overturning moment, if you look at the figure that rotates this way, trying to move the slope, is W times its moment arm x. The resisting moment is T times R. So these are the equilibrium of forces. Wx has to be equal to T times R. We know that the material, the shear strength, is equal to Cu because it's a phi equals 0 material. So if I now put that together with the mobilized shear strength, same as before, I have W times X has to be equal to T times R. So for W, I can calculate the weight. T, I know what T is equal to Cu times L. And if I put everything together, I'm solving for the factor of safety, and there you have it. For phi equals 0 method, with the assumptions listed, only moment equilibrium is maintained. The factor of safety is that equation. Whether that's okay for what you want to do, that's entirely your decision as an engineer. That's why you get paid the big bucks, so you can put your stamp on a document. And if it doesn't work well, they chase you. Okay? But still going back, just to recap before finishing for the day, you have to, for each method, understand what it does, how it's built, what are the assumptions. It's a rigid block, with circular failure circuits, undrained shear strength, what conditions you can use it, have an idea of the generic setup, and the rest is only moment equilibrium. We will see methods later that maintain both force in both directions and moment equilibrium for both slices and for the whole slope. You know, it gets sophisticated, but fundamentally, this is how you build the failure or the slope stability method given certain assumptions and so forth. Okay, so at this point probably I've said enough for the day as far as confusing the heck out of you. So I want you to, again, the way to study for this part of the course is go home, derive it on your own. There's a big mistake students make when looking at this is that they look at the derived equation, they look at it, yeah, it makes sense, yeah, that makes sense too, the other one makes sense. Yeah, of course it makes sense, but when you have to derive it from principle, then all of a sudden it's like, oh, was it this? No, it was something else. No, don't look at it, derive it on your own. That's the best way to do it. Because say, at one point I'm going to ask you, okay, this is the equation, wonderful. Let's say there is a load F or load P sitting here that is, maybe some distance A from that point or some distance B from the center of the circle. Okay, put that load into the factor of safety equation. And that's when hell breaks loose when it comes to doing it on your own, if you don't understand. I can put a distributed load, I can put a water table, whatever I want. Okay? Study good.